In our last video, we studied Euclid's algorithm to find the greatest common divisor between two numbers. Let's now see some of the consequences this important theorem has. Let's start with the first one. We have two integers, a and b, that are not both zero. So we can say that there will exist two integers, s and t, such that we can write the greatest common divisor between a and b as a linear combination between a and b. This is, we can write the GCD between a and b as some integer s times a plus another integer t times b. Let's look at the proof. What we're gonna do is go backwards in Euclid's algorithm. So let's call RL. Euclid's algorithm tells us that we can write RL minus 2 as an integer KL times RL minus 1 plus RL. So from this equation we get that RL can be written as RL minus 2 minus KL times RL minus 1. Doing one more step, we get that RL minus 3 equals some constant KL minus 1 times RL minus 2 plus RL minus 1. So now what we can do is we see that we have RL minus 1 here and here, and so we can write RL as RL minus 2 minus KL times RL minus 3 minus KL minus 1 times RL minus 2. We can rewrite this as 1 plus KL times KL minus 2 times RL minus 2 minus KL times RL minus 3. So we continue doing this until we get that R1 equals K3 times R2 plus R3. And so when we have done this L times, we get that RL will be equal to some number, I'm gonna call it star, times R1 plus another number, star prime, times R2. Then we get that B equals K2 R1 plus R2. Then RL equals this star number times R1 plus star prime times, and we have R2 here and here, this is times B minus K2 R1. Or we can rewrite it as star minus K2 times star prime, all this times R1 plus star prime times B. Doing one more step, we get that A equals K1B plus R1. Then RL equals star minus K2 times star prime times A minus K1B plus star prime times B. And we can just rewrite this as S times A plus T times B. let's see how this theorem works with an example we did in the last video. In this last video we calculated that the GCD between 120 and 84 was 12. So what we can do is look at the last two divisions we had, that is that 84 was equal to 2 times 36 plus 12. So from here we can say that 12 equals 84 minus 2 times 36. And the other division was that 120 equals 1 times 84 plus 36. So we have 36 here, and then we can conclude that 12 is equal to 84 minus 2 times 120 minus 1 times 84. We can rewrite this as 3 times 84, because we have 1 here and 2 times 1 here is 3 times 84, minus 2 times 120. So with the theorem we just proved, we get that 3 is our number t and minus 2 is our number s. We can write 12 as minus 2 times 120 plus 3 times 84. We have here, however, that it was minus 84. So what we can do is write it as minus 2 times 120 plus, and instead of writing plus 3, we write minus 3 times minus 84. So from here we get that s is minus 2 and t is minus 3. Let's have a look at this observation. If we have a and b, two integers, not both 0, and c is some integer, then what we have is that we can write c as a linear combination between a and b, if and only if the greatest common divisor between a and b divides c. This is an if only if, so we have to prove both ways. Let's look at the proof. First, let's prove that if we can write c as a linear combination between a and b, then the greatest common divisor between a and b divides c. So what we know about the greatest common divisor is that it divides a and it divides b. And what we saw in the videos of divisibility is that if we had something like this, then this number d would divide any linear combination between a and b. So then the greatest common factor would divide some integer s prime times a plus t prime times b. But this was our definition of c. So the greatest common divisor between a and b divides c. Let's now have a look at the other proof. If a and b divide c, then c can be written as a linear combination between a and b. So our hypothesis is that the greatest common divisor between a and b divides c. So then there exists an integer k such that we can write c as k times this number here, and this is the greatest common divisor between a and b. But with the theorem we just proved, we know there exists integers s and t such that the greatest common divisor between a and b can be written as s times a plus t times b. Then what we have is that c is equal to this constant k times the greatest common divisor between a and b, but that is s times a plus t times b. Let's distribute this multiplication, and we have ksa plus ktb. So we can now rename our constants as s prime, we can call it k times s, and t prime, we can call it k times t. And so we get that we can write c as s prime a plus t prime b. This theorem will be left as an exercise for you to prove. We have two integers a and b that are not both 0, and d a natural number. And what you have to prove is that the three following assertions are equivalent. To prove that three assertions are equivalent, what you have to do is prove that, for example, 1 implies 2, 2 implies 3, and 3 implies 1, or in any order. But the important thing is that we can go with an if and only if, that is the double arrow, between any two of these. Once you've proven that, then a simple observation will be that any number d that satisfies any of these three assertions is the GCD between a and b. That is only a consequence of all the theorems we have been working with till now.